Okay, what time?
6:30.
So I think it's gonna be raining a lot. Hopefully it stop. I was driving out there, so.
However, I can bring the pig on
Right, shadows, shaders.
It's right on University Drive. It's a very popular place. I don't think they take reservations, unfortunately. You have to go there. And it's pretty big. Hopefully, because it's raining, so we'll have less people to
Probably
go.
the big group is probably want it.
I don't think they take reservations, that's the problem. I'll call them. I'll call them before then, but I need to know how many people are going, that's the reason why. How many people they would have? Everybody's going, right?
It seems to be good, but unless somebody comes in and like they got a problem, tells us, we don't know whether it's working or not.
Yeah, we'll see.
So according to
Rafael,
whatever we can see
you're not
here,
going, right? You said they have something. You couldn't go.
I really wish I could go, but
And Jason, you're going with us?
no.
Okay.
I mean, I like to come, but the problem is it's
kids.
short. It's short morning. I can't rearrange the schedule,
Okay.
so it's very difficult.
Okay, we'll have 5, 11, I think. Make 12.
Yeah.
Okay.
I don't know if it's okay. Can you
Yeah,
see
that
enough?
looks great.
If I turn the rest of the lights off.
So Rafael is going to tell us the new modeling tools he's been developing for the past year, I would say.
No, more than that.
Year.
More than that. Yes. In fact, there is a little history I'll show.
Okay, so it's going to be so eventually we're going to switch to the new modeling tools very soon, hopefully.
Yes.
Okay, go ahead.
Okay. Well,
Thank
thanks
you.
for inviting me today to talk about this. I think I had mentioned in the past that we were working on this new tool, at least to some of you. So today I'm going to give you what the status of the tool is right now and a little bit of history, why the motivation on how and why we decided to move towards a different system. And as the title says, we're going to talk a new type of Kabul regional model. And this is just the beginning of the road towards a more comprehensive, community-driven regional Earth system model. So again, let me give you a little bit of history. In about 2011, we had the first actually official release of the CRCM, the tool that you know as CRCM. Now, of course, that tool was pretty basic. The coupler was developed in-house. The tool was essentially, and is essentially, coupling the regional atmosphere to regional ocean. Regional atmosphere is represented by WRF. Regional ocean is represented by WRF, by ROMS. It was within the coupler. There was a new bulk formulation for the near-sea fluxes, which basically was modeled starting with the core 3.0 surface formulation. It's pretty close to the standard ROMS bulk formulation. The grids of the two models needed to be the same. There was no regridding capability, and the coupling was done with files, which means the information exchanged between the two models and the surface was done through files.
When you said core flux, so you recomputed the flux, and we didn't use the word flux.
No, this is the first ever version.
That
Yes,
version.
yes.
So they were not consistent.
No, that is true. Yes, yes. It was forced with the core 3. Yes. So we were using diagnostic variables at the surface to compute, like U10, V10, T2, and Q2, to compute the fluxes. Soon, I mean, pretty briefly after that, we included, the option of including actual fluxes from WRF surface layer to make it more consistent. So the model was presented in April 2012 at the Software Engineering Conference of the Software Engineering Assembly, which is an organization of NCAR, UCAR, rather. And in summer 2012, the model was actually used as the main engine for the Kabul regional forecast system. They were used to help researchers. They were working on figuring out a way to predict oil spill patterns in the Gulf of Mexico. Working on this BP funded or GOMRI funded project. So the funny thing about this was that we actually, this was a kind of a real life test or challenge for our model. We were able to predict 2 hurricanes, which of course we weren't expecting, in the Gulf. The model ran between the end of July and the beginning of September 2012. You can find output and plots at this address if you're curious. And I have to say the model did a pretty remarkable job in predicting the path of Hurricane Isaac. So we used again this model as part of the couple regional forecast system. So we turned it on again in 2013. There was a blowout of a gas rig in the Gulf. The name of the gas rig was Hercules 265, and it was off the coast of Louisiana. And in fact, this is the location. Again, we turned on this couple regional forecast system with CRCM, and you can find some plots of the forecast at the same address. And I mostly kept working on the model constantly between the beginning and up to 2015 to last year, and I added improvements constantly. In 2013, I added the new release of WRF at the time, 351, including additional surface layers. At the beginning, the model was able to exchange data only using the standard MM5 surface layer. Now you can use other options. Regridding was included for the first time, and it was done in a conservative way. In 2014, I added more improvements. We started to experiment with an SST filter, which was parallel. In fact, the work of Xiaohui here, it was based on that. I've included the possibility of using parallel CDF and WRF, faster coupling, split coupling files in chunks to make it, again, faster, more I/O performant, because coupling is still performed through files. I included the possibility of using salinity restoring and 3D dungeon in ROMs, which we didn't use at the time. Now, the latest version of this is a version that I call 227 beta, because it's still not official.
So the 3D dungeon is not a standard feature of ROM?
Of ROMs, yes, but it wasn't activated in the coupling environment. So I basically had to do some work to activate that.
Why does the coupler get involved with the 3D dungeon?
Because of the way ROMs has to be configured when it's coupled. So many of those standard things were turned off for safety. And so then slowly I started turning them on once I was sure that everything was working. So originally this was turned off. The latest version includes new configuration options for a model that Sao was working on, the idealized channel model. I think I can, if I'm not correct me, please. And that has periodic boundary conditions. And there's also minor improvements, including some bugs that were in the regrading procedures, and also a way to build the model partially, which means the model still consists of WRF and ROMs. When you build it, you have to build both codes. But now it's not. I mean, in the past, you could avoid building one if you knew how the code worked. Now I made it easier for you to build either one. So it becomes just faster.
Did you have a version which didn't use files?
Yes.
That's the one.
That's the one I'm going to talk about. But
Okay.
That's a
but,
7.
right. So we're going into there. I just want to mention those 2 publications that Xiaohui wrote, and they're based on partially CRCM. In this case, mostly the SST filtering. In this other case, instead, I believe she used fully coupled CRCM simulation for that, right?
No, not in this paper.
Not in this paper?
In fact,
And that one, no.
We're about submitting another paper.
Okay.
Which uses the fully.
Okay, then it's another one. But anyway, I think now you're using the model as a fully coupled.
That's right. You
All right.
also follow some.
Well, okay, thanks. That tells you a lot about how much I read this paper. So here's the story towards, the new road we're taking. In fall 2011, we started a collaboration with PNNL about trying to study what the origin biases in climate models are, and especially focusing on tropical Atlantic and SST biases type. During those discussions, we decided to shift our development to a different version of the couple model, which included also an active land, which now, by default in CRCM, is included as part of work. Okay, so there is no external model for the land. So by doing that, we decided to use a different coupling framework that is based on CSM. And this was the reason because, first of all, it's a framework that's been developed by the community, tested thoroughly. It might be helpful in terms of including other models or model components that are part of CSM or regional versions of them. And also, it will be helpful, ideally, to improve or facilitate a potential integration between the two models at some point, for instance, for downscaling simulation. The results of this were presented at the 19th annual CSM workshop. This was a first version ever, 2014 June. And so we called it with this acronym CLESM. We're not there yet, but that's the goal. In any case, in 2015, we have actually a fully revised version, which is final. It's functional, fully functional. It includes multiple configuration options, and it's fine-tuned towards higher resolution regional climate simulations. It improves actually the original CSM's couple 7 configuration type. It improves the number of options that were present in the CSM couple 7 framework. It adds new option. It adds a new way of configuring and building the model, which I will show you in a second. In 2015 summer, CRESM is ported to this new architecture, Power 8, that is being developed by IBM. This architecture is characterized by a very high memory bandwidth between processor and GPUs. And actually is based on the Open Power standard, which is a community, for the first time ever, is a community standard for computer architecture. And I have to say, the model worked pretty much right away. There's a few things you have to change. But so now the point of this is it can also build and run correctly on this type of architecture. And then in 2015 was included in a hybrid framework for real-time 3D visualization and computational steering, which means there was this framework. There was a 3D visualization framework that was developed by IBM Research, and we embedded our model into it, which means you could actually start and stop the model within this framework through a graphic user interface. And by doing that, you could change, to some extent, the initial condition. I mean, we focused on modeling in this demo, which was done at the Supercomputing Conference 2015. And the slide demo, the way we change this initial conditions is to just change the position of potential oil spills. Of course, it would be very difficult to change the entire 3D initial condition, just by clicking on the screen. But you can do that if you come up with some useful ideas. The framework allows you for that. So why did we choose the CSM couple 7? Well, again, this is the state-of-the-art architecture that is available nowadays. And it's built on libraries that are maintained in the community and also by national labs. It provides standard interfaces to model components, which means it becomes easier to some extent to plug in external components for physical processes that you want to represent. For instance, for wave models, runoff, things like that. By doing this in a standard way, the code becomes much more portable, and it's easy to work on it, and it's easier to develop. Also, this type of interfaces are fully accepted by the community and by developers nowadays. So if you want to take your contribution and make it public, it becomes an easier way to publish that. Also, this coupling infrastructure actually scales pretty high, up to over 10,000 cores, which means the scalability potential of this interface is being tested thoroughly, which means the coupler is not going to be responsible for slowing down our model very much. And it's not going to be responsible for not having a model scale. And since we're looking at higher resolution simulation, that is a very important point. The model builds as a single executable. Is it also compatible with this framework that is pretty much well known, the ESMF framework. So it's ESMF compliant, the Couple 7 framework. And again, allows for connecting to a broader community modelers. And ideally, you can interchange global and regional components within the same framework. So you can do a lot of things. So the framework itself, that's another positive, that's another plus of using the CSM Couple 7 framework, already provides methods, functions to remap or regrid surface quantities. So to communicate between different physical models. So this is called multi-physics simulations, right? Because you have several processes that interact among each other. So issues like load balancing are very important. Issues like communications are very important. They need to be done efficiently, and the Couple 7 is being tested for that. It is the best thing that is out there. It's one of them. It's not the best, probably, but it's one of them. So there is standard procedure and tools that you can use, for instance, for doing regridding and remapping. So that already relaxes one of the requirements of the old CRCM, which means the grids don't need to be the same between ocean and atmosphere. You can use different grids, and you can use remapping in several ways. There is a conservative remapping, there is a bilinear remapping, and depending on the quantities, you can choose a bilinear, for instance, for vectors, and conservative for fluxes. So you have that kind of flexibility in this framework. Also, yes?
I have a question. Does that mean that we do not need to provide the remapping
No, you do.
files in this new version?
You do.
Still need to.
You still need, yes. But you can provide, like I said, a bilinear mapping file for one quantity and a conservative mapping file for another quantity. Okay, so yeah, it gives you a little more flexibility in terms of say, the remapping vector is not the easiest thing. Fluxes are conservative, so we know how to do that, but vectors are tricky. So
What about wind stress? That's a vector.
that's the point.
It's also
Yeah.
a flux.
Well, it is a vector flux. It is a vector flux.
Right.
I mean, if you consider as flux.
Which one would you?
So they suggest to use bilinear for that, and that's what they use in CSM. So I mean, eventually, see, that's another question. The question is, this framework has been used a lot for large-scale simulation and global models, right? CSM. Resolution so far wasn't very high. Now we're getting there. So all those things are based on experience. So now our model instead deals directly with the high resolution. And by doing that, some interpolation might change a little bit the game. And you have to be even more careful about that. So that's why we included that to provide more flexibility.
So is it tri-grid? So CI is on the ocean grid?
Yes.
CI is always on the
Yes.
ocean grid.
Yes, I think so. Except, well, traditionally, yes. But then in the new CRESM, you can use CIs from WRF also. You don't need to use CIs from the CIs component.
Okay, it's confusing.
So you basically turn it off and you use whatever WRF provides as CIs. So one other good thing about this framework is the fact that the layout of the processor that you use for each model components is pretty flexible. And this is something you should determine empirically. There's really no rule. It's all based on load balance. Depends on the architecture, depends on the machine, depends on the size of your simulation. And so the number of cores which are assigned to the atmosphere and, for instance, the ocean, or if you include land ice, or if you include land, it's basically depends on your problem. Okay? So the good thing about the driver is the driver can see any of the components, including the coupler. Why there is a driver and why there is a coupler? Well, it's sort of a semantic thing. You can think the driver as the coupler sometimes, but the coupler is basically responsible for the remapping thing, for connecting stuff. The driver is responsible for driving the flow. Okay, so the driver is basically a wrapper which drives the main flow of your simulation. And then the coupler is responsible for calling the model, remapping.
And also computing
sending
the
information.
fluxes, right?
Yes,
All
and
the
computing the fluxes too.
I mean, that
Yes,
was
because
the key thing.
the other component that is included in here is actually a bug formulation for the air-sea interface.
So my understanding is that all other components, they don't compute the fluxes anymore.
No, they don't. Well,
They just pass the variable to the coupler. There's only one place you compute the flux.
exactly. So the coupler,
There's one flux.
the coupler deals with the surface interfaces.
Right.
So the surface interfaces that are active right now are the air C and the air ice, I think. We
Okay.
deal with,
Not air land.
no,
If you have a separate CLM, then.
no.
separate
The
line model, then-
CLM computes the flux.
but
Yes,
within
yes.
CAM.
No. It has a bulk formulation
So
inside
it does go
CLM.
to the coupler.
Well, it depends on what it means when you say it goes to the coupler. The coupler is involved all the time because it needs to exchange the information. Whether the coupler takes in some parameters and then computes the fluxes and then passes those fluxes that he himself computes to other models is one thing. In other cases, the coupler doesn't really compute the fluxes, just take those fluxes from the model itself. And in this case, in the
So
case of
land
CLM,
flux is not computed within the coupler.
it's only, like I said,
It's only
it's
the
the air
ocean.
C interface.
How about
And it's
CIs?
something about the CIs. Too.
The
The
CIs
CIs too, yeah.
So anything to do with the ocean.
Yes, but again, this is standard in CSM coupler 7. This is not standard in our model. I mean, you have the option of choosing a different interface. Okay.
Are there any lake values or anything?
Yeah, that too. There are, in fact.
What the flux?
In
is
the land?
computed- Yeah. over
Yes.
the land.
Oh, yes. Oh,
Is
yes.
that computed within the
Yes.
land model?
It changes
itself?
the roughness length and it changes the
Okay,
flux.
so it's not computed in the coupler.
No. Everything is computed for the land.
Okay, so only the ocean.
And again, this is true when CLM is active. In our model, we can use an external CLM, community land model, regional, but we can also use the land component in work. So in that case, of course, there's no coupler communication because there's no need for that, all right? Questions here?
I have a question on load balance. When
Yes.
people do load balance, it's a trial and error.
Yeah.
But ideally, what you should do for load balance is run each model with data for every other model. Get timing per time step,
No,
then we finish. Get timing per time step for
Yes.
each model.
yes,
Assuming all the other models are data,
Yes.
providing data.
yes.
Then you can run an algorithm that will give you the load balance, right?
Yes and no, because the problem is once you have two models active, for instance, instead of one, then you'll see delays because of resource competition. And so those delays, you can use a data
what
ocean
resource
is much
would they-
faster.
What would they?
Communication
what resource would they
delays.
compute for though? That must be an
Even I/O, they have to write to the same file system.
But they're on different cores. on different
Doesn't matter. The
nodes.
file system is the same. And the other thing is the data models are very simple. So really,
That's fine.
computation is right.
No, but
Right.
that's by design. So
So-
you have a data model which is
Right.
trivial. And
That's
then
why-
you get the time per time step.
Yes. No. Roughly, I understand.
But I think that should be the starting point.
It should be, but I don't know if really it's going to lead you. You know,
No,
of course,
then-
you do have an idea of how much a model it's or needs in terms of cores.
Usually it's when you
Right.
ask somebody, that's how you. do it.
Yeah, yeah.
But they know,
But
if we just download the model, is there an obvious way to get the, at least the initial?
no, in that case, it would be good if you can run the model on its own. Like I said, either using data models for everything else, or you can do just forced.
So I always hear people saying, well, I tried this and I changed it.
Right.
It seemed very,
Well,
I'm not sure they're optimal. They just stop. at
no, they're not
local
optimal.
They're a local minima. I'm not sure. that they go-
Absolutely, and that's why I'm saying, you can do that, and that gives you an idea of how much cores maybe you need to assign. But then you do assign those cores, and then you see the balance changes.
Right.
Because of delays, because they run on different machines, and those different machines are not synchronized, first of all. They run other processes. There is I/O contention occasionally. And so once they introduce a delay due to the coupling, which in this case actually exchanges more information than in the case of the data ocean, then the balance can change. So yes, you can try that, but it doesn't mean that gives you a rough idea. But you still have to adjust it.
I think what the NCAR people should do is they write some code that while the model is running, it tracks the delay statistics and says, next time you run it, use this. load.
Maybe that, yeah. The fact that some of the
Because then
noises,
you can collect data while it's running, right?
some people do that actually, but it's a statistical noise. Some of the
Right, but
noise
you
is
can-
just
you can-
statistical, so
you
you
can
can't
deal with
really,
the statistics.
I mean, you can assume a
Yeah,
uniform
let's see,
distribution.
It'd be nice to print it out at the end of the run. This is the current load balance, this is the
Yeah.
better load balance. It doesn't do that. People are sitting and guesswork.
Well, okay. You know how those models work. You know how those models are written. Those are community-based models. It's going to be very hard for something like that to be
Well,
implemented.
Next time that we are.
It would be great, but
Yeah,
I don't know if there is the sophistication to do that.
that would be a couple of jobs to come up with a predictive.
Yeah, it could be, but it doesn't mean that the model is able to achieve that. Because then you scale WRF and you add 100 more cores to WRF. And the scaling curve is flat. Are you going to change anything? No. So that's why I'm saying it's very hard to predict, even by running each model independently and then coming up with the number of cores. Because if it does scale, or if the scale curve becomes flat at some point, how are you going to predict it? So that's one issue. But one thing I want to emphasize here is this. So the coupler 7 actually has the possibility of two type of, say, coupling between the ocean and the atmosphere. One is the standard configuration. And so I know that this is hard to read, but mostly, I just want to point out the things that you need to see. You advance the clock, there is a big loop, time loop. No? The model starts and it advances the integration. You prepare everything you need to prepare for the ocean, and then you run the ocean. The result of the ocean running goes here. And then you go back. Prepare everything you need for the ocean. The result goes here. It's merged, of course, with whatever is coming out of those other models, and then go up. Isn't that strange? Look at that. What is this done? This is done before this point.
What is that, ATM?
This is basically the RC interaction part, the fluxes. So this is merged at this point. So, okay, the fact that there is this arrow, this path, it doesn't mean that, this is one portion of the code because it's parallel. The other portion of the code goes through here or goes through all these other paths, right? But look at where the sea surface fluxes are located, which means the ocean will always be delayed. At least the forcing that you communicate to the ocean will always be delayed. Now, there is a way that you can make it tighter a little bit. So reduce the delay, at least by one coupling step, with this different optional configuration, which is standard in CSM _7. So the ocean run, instead of coming the result at the end of the loop, they go here. Fluxes, go back. This is still delay. Why? Because you're not forcing the ocean with whatever is coming out of the atmosphere. So you're still a step behind.
So this is 2 steps behind that one.
Yes. You can't get out of that.
Well, 1 step behind, you cannot get out.
You can, and we did. You have to change the sequence. That's why, when we do regional simulations that, don't take 100 years, but they take maybe a week. No? Everything needs to be in sync. Right. So you cannot introduce artificial delay.
Both components be consistent. Maybe there'll always be a delay, right?
No. Well, the fact there is some sort of intrinsic delay, but it goes in both directions, in the ocean and the atmosphere. In this case, the delay was on the side of the ocean all the time. So what I did is to move the optionally. A configuration time, you can change that. If you want to stick to the old sequencing scheme, it's fine with me. But then you'll notice that the forcing is delayed.
Okay, but there's a coupling interval and the time clock interval is a time step interval. Coupling interval.
This one, the
Clock.
time loop, basically, it advanced by the smallest of the coupling intervals because
But it's still
Coupling is not the
it's
same.
not the model time step.
Smallest coupling interval?
because you have
What do you mean smallest? I mean,
You have
each
several
model has
models,
its own
right?
different time step.
right. So you take
Yeah.
the smallest one.
The line
So
is
it's not, then it's not really coupled. Right? If you take the smallest component.
Well, the smallest one has to
like this
advance.
atmosphere,
If you
Yeah,
line
it's
is-
that's
probably
true.
the smallest thing.
But it's not coupled in the sense that
There's no
the smallest couplet time step. So
So-
there is
so
at least
question-
2 models that are connected.
So the question is that when you run the atmosphere model, we're seeing a couple of times that.
Yeah.
Do you update your SSTs?
Only if they're needed. So only if the ocean is ready. Otherwise, no.
Right.
So each model runs internally.
Right. So
if there is another model and it needs to be coupled.
The SST essentially is a constant.
So because everything is computed here.
Also, you
At this
move that
step.
Atmos prep there.
Right. So this is optional. I mean, this is what we need to do. This is how we run the CRCN. Okay.
So did you check with NCAR people why they did it the other way?
Let's not talk about that.
Why did you get some kind of noise?
No, but
Well, why not?
I will check. I will
We're
check.
officially collaborating with them.
Yeah,
They
then
should
I
know.
will check now.
You're among friends here.
Yeah. a lot of friends.
Now they're our partners, so we should let them know
You can
what
turn
we
off
did
the
with it.
Google Hangouts and talk about
Yeah,
Oh yeah, I'm recording.
it.
Don't ask me questions
actually,
like
you
that.
know, Gokan's gonna come
Off the
in
record.
2 weeks.
Uh-huh.
So make sure that we block the time talking to him.
Well, yeah, remind me.
He's not the person doing the coupling. I
But
mean,
he
he'll
would
be the
know,
largest one,
but he'd be familiar.
but he should know about this stuff.
Oh, but no.
Tell
Look,
him all the stuff you have
yes.
done, and we'll
But
talk to him.
but we need to be honest, and the honesty is, I'm speaking to the mic. The honesty is that this was done for something that was different. We're not doing global simulation. We're not doing global simulation that lasts for hundreds of years. Okay, so-
I can see philosophically.
Right.
There's a difference when you do the global.
Right.
Scale simulation versus the regional scale simulation. The way you do the coupling.
So the reason I'm asking is
Right.
sometimes whenever you look at code, there is some important reason why things were done certain way, and sometimes it's
Right.
not documented. It's
Absolutely, and I
I'm
can
sure
I
there are
can
lots of
guarantee you.
discussion and thoughts went into that.
Absolutely.
And then
They
so
did this.
But then we don't want to rediscover that important reason.
But we're not. We're just using a different scheme.
But
I mean, we're not
there's
taking
our
anything away
reason.
from this.
We have our reason why we do the
Right.
coupling our way, right?
Right. We're not taking anything away from this. This is just a configuration option.
In fact, I don't even know when they do their hurricane simulation in global coupling model, how are they going to do it? I mean, they must be doing.
Well, they definitely won't change this sequencing
I
scheme
don't think
because
that-
it's
I
ingrained.
don't think they care about ocean feedback. They're just
Right,
looking at-
right. Right.
But the hurricanes, you probably have to considering some kind of ocean feedback.
So we're not in camp. They're just looking. It's very exploratory, right? They're not looking.
That's why last time when I visited NCAR, I was talking to Joe Tribbian. He doesn't believe the whatever the camp gets hurricanes, actually hurricanes get it
Well,
all.
they do all kinds of strange diagnostics.
All
I
right.
think that's not the biggest problem, that they don't get ocean feedback.
Yeah.
They don't get hurricanes in their land.
Yeah, I was talking to Julio, and he was talking to me about. You remember they get this Category 5 hurricanes all the time.
Yeah, but they're
Remember
looking at some
lower
different
resolutions?
levels. They're using different diagnostics.
And they say it has something to do with the way the momentum, the wind stress, was passed to the ocean. And they changed the wind stress, the configuration. Now actually they don't see the Category 5 anymore. Really strange. So anyway, but it's good things we talk to them.
Yeah, sure. In fact, I think Julio was the one talking about this issue, and he was concerned about the remapping step because of the wind stress. Yeah.
Which thing, right? Can come
Yeah.
back again.
Well, in any case, I mean, this is just example. I'm going to skip to this very quickly in how you can achieve load balance with different configuration among models. If this is the processor and this is the time, you can arrange them in different ways. And of course, it's not going to take you 33 seconds for a run. So just dismiss that. But this was published. It was just part of the original work. So how do you use this framework and add components? There's two main ways, right? You can replace a component that was already there, like the ocean or the atmosphere. And in that case, you shouldn't touch the Coupler 7 infrastructure. Or you can introduce a totally new type of component, which was present before in CSM. And then in that case, unfortunately, you have to modify at least the driver, because the driver has to call this new component, which wasn't there before. And by doing that, of course, you're going to modify the sequencing to some extent. In both cases, though, you have to develop software interfaces or standard software interfaces to the new coupler. And those interfaces is basically components or functions that call your component model, and there's three actions they can do: init, run, and finalize, stop. So you do an initialization step when the model starts, you run, and when you run from time 1 to time 2. So you have an interval of time, and then you stop it. You finalize. That's all you have to do. And that's the basic scheme. You couple, import, run, export. Export means whatever data you need to exchange, for instance, interface data, needs to be exported to the coupler. Okay, so this has to be embedded in your run
So when you
component.
introduce a new model component, one coupler, I mean, let's say new model component.
Yes.
For ROMs. But
Yeah.
When the coupler expect you always have an ocean model, atmospheric model.
As it is,
So then if you have a new
yes.
component, what category would it fall under?
No, you pick it. You know.
Yeah, so you don't have to have all the models. You have
No, yeah. But the coupler itself always expects to have an ocean and I think an atmosphere,
That's why I'm wondering how it pigeonholes this new model.
and actually probably land too.
So in the original version, right? So let's say ocean atmosphere, so
Yeah.
the flux is a computer within a coupler.
Yes,
But a Wolf model also computes its own fluxes.
yes. Now, in
Right,
this
so,
new version,
so now you
yes.
actually have two fluxes.
Well, when you pick WRF, you're not going to compute CSM.
So
fluxes.
what do you do in that case? You actually
You bypass them. You don't call that
you don't
function,
call that a
basically.
Wolf routine at
Right.
all.
the CSM routine.
No, I know that, but if you use the coupler 7, right?
Then
so
you don't call the WRF
You
routine,
don't call the Wolf routine.
Yeah. And you make
But
sure
can you
that.
actually call the Wolf routine and then pass the variable? I mean, would that be just not have?
And
Well, the reason I'm curious to know how different those fluxes are.
you can do it. You could compute it both ways because you can turn one off, run, and turn the other off,
Isn't that,
turn the
that
other
should
on,
be
and
very
run.
useful, right? The way the coupler 7 computed the flux.
Yeah.
And the way originally the.
Yeah, but you can do this.
Must be different.
It is different, yes. But you can do this with separate runs. I mean, ideally, you could do it in the same run, but
But
It's not part of the code,
We
no.
never looked at it.
I don't know how that would
But
make
we
sense.
actually, you did a test to see
Yeah,
that the two
yeah, yeah.
schemes do give you different results.
Right, and the thing is, if they're not connected, there's no feedback. I don't know if it makes a lot of sense
And
to
the other way-
run both.
Right.
Right.
The
Because
other
only
thing
one is active. Go
I
ahead.
want to ask you is that in our old version of the model, I don't think we used the average.
No, that's true, yeah.
So we used instantaneous value.
In the CRCM, there is no average of fluxes.
So
So the interface basically is not average.
the coupler 7 uses average file.
The coupler 7 by default does it.
Coupler step is much longer than ours.
Yes, because they run long-term simulation. But in this new version of model, regional model that I'm showing you, you have the option of turning that off. So you can pick. You
Not
want
using average.
right. You want to use a snapshot, use a snapshot. You want to use an average file, use
And you
average
added
file.
into that.
Yes,
Okay.
yes. So again, like I said, this extends traditional capabilities because we've also introduced the possibility of using WRF's embedded surface schemes, like the traditional MM5, revised MM5, blah, blah, blah. You can also use the NoLN model, WRF, instead of the CLM external. And there is this new thing that is kind of interesting. So you can take a data model and you can carve out a nest and you embed a ROMS model into this nest. The grids have to be the same. Of course, not the domain, the grid. You're doing this, this allows you to run a larger domain because it won't be as computationally costly as if you were running just ROMs. But it might be helpful to examine just some areas that you're interested in. So if suppose you have good boundary conditions for the ocean, this could be an option that you should consider. And the rest of it is basically a data model or even a slab ocean model. So if you have data to configure that, you can use this strategy. This is being implemented into the CSM and the CREST as a new component that is called extended ROMs.
Did you do this or did they?
No, I did this. So here is a summary very quickly. Coupler, WRF, atmosphere, ROMs, ocean, CLM version 4 for the land. The CLM actually is being supplemented with a new scheme for variable infiltration capacity that was built at PNNL. There is also CI's component, which works. We haven't really tested, so it might work, but it might not be very meaningful. There's also the option of activating, let's say, Mozart for stream flow and stream temperature. There is a potential of using water management, that they're not included, those components. This one actually is, but we have never turned it on. One thing that, okay, let me skip to this and then I go here. The code has been developed in strict compliance with the developers of CSM. So all the guidelines have been followed to make sure that this code can survive, it can be extended. It's also in compliance with ESMF, which is becoming more and more important, at least with the NOAA and DOE efforts. And there's two new things. One is, if those of you who use CSM, you know how the configuration can be. You know how the building process can be. You might like it, I don't. So I've completely changed the way, you can still use the old way, but I completely changed the configuration and building step to make it much easier for us. And this is based on standard GNU build tools, which are configure and make. So anytime you download some, for instance, software components or library from the web that is standard, you know that you have to type configure, and then you do make, and then make install. Same thing you have to do now for this model. So everything is easier. And to make you even happier, look at this. In the past for CRCM, you have to open the ROM's configuration file, so the header file, add some keywords that would work for the couple model. And you had to be careful because, of course, you weren't sure what type of keywords. So I provided you with a template. In this case, you just need to forget about it. You use the original uncoupled header file for ROMs. And this configuration thing will do it for you. Of course, it would be worth if you check it at the end, after this is done its job, to make sure that there's no mistakes. Yet, you have a fully coupled ROMs header file from an uncoupled header file.
What about WARF header file?
You don't need header files for WARF.
It's the same couple on top.
Yeah. No, I mean, the main configuration files are embedded into this configure process. And so the configure is able to pick for you which one you need. But for ROMs, you need to include separate physics schemes with this header file. And so you need to be able to change it yourself. So with this configuration thing, helps you basically translate your uncoupled ROMs header file into a fully coupled header file without too much work. So again, this is another
in your previous slide, the FVCOM, is FVCOM already inside the?
No, FVCOM is not inside.
It's not.
Mozart is not FVCOM,
So
but this could be included.
We only have Mozart, right?
Yeah, except that we haven't really tried it.
Yeah, FVCOM might be very useful for inundation for
absolutely.
the sea level, regional sea
Absolutely.
level thing. So
Absolutely.
that might be something we want to
I think we should.
think about.
I think absolutely. Yeah. So this is just to summarize the schemes. The physics schemes this time are available within each model. And in WRF, when you couple an atmospheric model, to the couple, you need to provide some sort of information. And so this sort of information has been provided for the RRTMG model, radiation scheme, and count radiation scheme for both short and long wave. And there is a spectral way of computing the albedo that is also available, which is standard in the CSM. It's optional in this model. You can use this fixed albedo if you want. There's also a configuration that tells you, okay, I want to configure this as if it were CRCM. You just set that, and it will do it. Okay, so we have WRF land model. We have different surface models within WRF, and the other things you already know. So briefly, again, we have a fully automated configuration system that allows you to type almost just that, configure, make, and make install. Components can be enabled or disabled through this interface by just doing enable or disable and the name of the component. Physics option can also be added, configure, activated, deactivated, enabled, disabled with this type of option. Syntax, and so, for instance, if you want to use the surface layer from WRF, you just do this, equal WRF. You want to enable ROMs as an ocean model, then you do enable ocean equal ROMs instead of data, for instance. And in that case, you have to provide a header file. And so you do with roms header equal. This will generate automatically a new header file, ocean.h, in the build directory, same as CRCM. And it will ask you, make sure you check it before you type make.
So when you disable a model, is it replaced with a data model? How is
It depends. If you disable, it's null. So it is replaced with a stub. It's not a data. If you want data, you have to tell them. So, and in fact, you can see this here. So you have, when you do configure, there is a long list of options. So I took whatever we're interested in. These are, performance options. You can actually run this in a hybrid mode, mostly by configuring WRF in a hybrid mode. This really works on the POWER8 architecture. You don't have to worry about this in regular x86 architectures. You can make available atmospheric models WRF or data by saying enable at equal WRF, equal data. Enable ocean equal ROMs, XROM, extended ROMs, data, and stub. Stub means null, there's no ocean. Enable CRCM, again, you can configure this as CRCM. You can change the surface formulation from here. You can enable the flux average. By default, it is enabled. You can disable it.
But this is all within the coupler 7 modular scheme, right? You can do
No.
some
Yes.
of the.
Yes.
I saw we cannot do the data atmosphere.
The data atmosphere, it's there. It's not, doesn't work for WRF.
But it doesn't work for.
If you have WRF
exactly.
data files.
That's right.
So that's what we
You
need to
choose
change.
it. That's something we.
Right.
We still need to
But,
work on.
but you can use, for instance, files that were generated with the coupler from a different simulation. In that case, you should be able to read it.
Right.
So any run done with the coupler can use the data.
You can save the interface.
That,
Yeah.
That's the idea.
Yeah.
But you can, since we can't pull the WRF formula things into the coupler 7 yet. Yeah. So it's,
Yeah.
we can do that yet.
So the other thing you can pick is the orbital parameters, because they might be different between your RAN and WRF. The timing and where the radiation is computed. For instance, WRF computes the radiation within an integration time step in the middle. I'm sorry, between a radiation time step in the middle.
And you mentioned to me there's something coupler 7 wasn't done correctly. Wasn't that the some about the radiation things? You had to change that.
Yeah.
Below.
It was.
It's not albedo.
No,
It's
it was
actually the
some
solar angle or
synchronization.
something. Isn't that the solar angle? There's something about the solar angle you're
Yeah,
not very
it
happy
was
with
that. It was something about the synchronization
Yeah.
of the yeah. Anyway, all those things then become synchronized between model components. So that's why they are important. You can change also the shortwave radiation timings. Like I said, you can change the scheme for computing the surface net shortwave radiation.
I'm wondering, Rafael, I'm wondering if once we get all the bugs out, even just writing something about the comparison between the WRF, the MM5 modulator versus the coupler 7.
Absolutely. No,
Itself is actually interesting.
I think it is interesting.
Or just write about that. would be very
I
interesting.
had an idea of doing a paper on it, but we have to produce some
Of
numbers.
course, I mean, there's no absolutely choose. We don't know which one is really
No,
right.
but they're tuned in different ways. So
I would say first do that with the column model and then do
that's
Right.
what I was thinking. Yes.
the column model.
Yeah. So anyway, you can see you go and go. And so you can enable ICE, the variable infiltration capacity in CLM if you use CLM in land. Same things for optional packages. These are the libraries you need. You need to pre-compile or pre-build the parallel I/O library. That's the difference with CRCM, but those are required for CSM, and the MCT library. So they come with the software, and they come with scripts for you to pre-build it, and then you have to tell them this is where they are. You give them the path, and it will recognize it. Then you have to provide the path for NetCDF and parallel NetCDF if you want to use it.
And the TNCDF, does that work for ROMs?
No. And then this is, of course, as I showed you, if you want to provide the header.
So why doesn't it work for ROMs?
And,
The community just doesn't want to do that anymore?
No, they use the HDF5,
Oh, okay.
but it's not really working. So these are variables. You shouldn't touch any of this. because the configure script is able to probe your system and try to figure out what compilers you have. So if you're not happy with the choices that the system made, then you can change. You can use this variable to say, no, I want this compiler, I don't want this other one. Okay? But automatically, you shouldn't worry about it. Okay? So this has been tested on several clusters, by the way. So pretty much this is where you're going to run. So I think the default choices are probably good ones for you. But anyway, you can change it.
But so in this case, we do not to set up the environment.
Oh, no, you do have to load up, because if they're not in their environment, of course, it can't see them. The script cannot go and look for them.
What if there are multiple options?
It will pick the best one. Yeah, but you can change that. So if there is Intel MPI, if there is Fortune MPI, if there is, I don't know, in MPICH or in MPICH MPI, it can pick the best combination. All right, so this is practically how you would do it. So you do configure. If you type a prefix, if you include a prefix option, this is where all the files, the final executable will go, instead including configuration files. And then these are your choices, right? So you can use actually several versions of WRF, except that now we have one, so it doesn't matter if you use WRF or WRF 351. It will always be 351. Land, in this case, we're picking the land from WRF, so that's what you have to say. We're using the surface layer from WRF. We're using an extend ROMs, which uses this configuration file and uses a data ocean for the rest of it. Data ocean is very easy to build, at least if it's not a slab ocean, because you can use WRF's lower boundary conditions. And there is a Python script that will convert that in a way that the data model will read. So it basically replaces the SSTs periodically and interpolates linearly, if you will.
Did you actually test the slab ocean model yet?
No, I haven't. So if somebody wants to test it, that would be great.
Actually very useful.
That would be great.
Coupling slab ocean
Yeah.
model to work itself.
Yeah, I mean,
Because I haven't seen anyone really.
yeah, I think
So
we
are you
can
using the
test.
Slavotion model to compute CSM?
Yes, yes.
That changed the way you compute the Q-flux, right?
Sorry?
How the way they compute Q-flux for the Slavotion model.
Means now they take the mean from the coupled.
But I think this is going to be, the region model is going to be more complicated.
Yeah.
You have to be more careful. Maybe this restoring approach is actually a better one.
You're less iterative, right?
Right, you have to run many cycles.
So I like to just expand the SST and then the.
Yeah.
But if you have a really high resolution SST,
Mhm.
suppose you also have the diagonal cycle.
The Guangming had a different issue. He was changing the ocean.
Right.
So you have to do the relaxation. But the general problem, the reason NCAR changing because CI, the CI is.
Because Ed Schneider has a student who is trying to compute the same way as what they do. I mean, they're using the old technique, just specified SST calculator dependency, and they come up and they run the model with the Q-flux that computed that way. The SST looks terrible.
Do they have CIs?
I think they fixed the CI, specified the CI.
Because usually to fix CI, it's the.
But the SST is not even in the high latitude.
Why
It is the low
changing?
latitude.
So they've been doing this technique.
I don't know. There's something really
No, but
wrong.
NCAR always takes the dynamic CIs and
Yeah.
thermodynamic CI and then it kept very nice.
Yeah.
Q-flux doesn't work that easy.
Right.
Yeah.
So once you've done your configure, then the system, checked everything, and if everything went well, you get a long page of output, and these are basically a summary of the configuration details that you use. So in this case, we use the atmosphere, WRF 351, land, inside WRF, ocean extended ROMs, CIs was the WRF built-in. Doesn't mean that actually we use it, but we keep that option open. The ocean atmosphere surface layer is WRF built-in, and we do use averaging of fluxes. Solar angle, as those used in
I
CSM.
remember there's something about it.
Yeah, we can choose, but that's what we choose. That's what we chose when we configured the model. The shortwave radiation timing is mid-step. What's so funny?
The model use a lot of components.
It does, yeah, and also a lot of options. I know.
What is SGLC and what is SROF?
Oh, it means stub. Runoff.
Oh, runoff.
Yeah.
GLC is.
Glacier. Because, you know, the ice would be the sea ice.
Because over time, it keeps increasing. the
Yeah,
amount of-
yeah.
This thing you can see it's going to become it's more and more complicated.
Yeah, no, of course.
There's going to be more. The list is going to be
What
longer.
about the calendar? I mean, sometimes
Well, then it's going to be a wave model maybe or something
Well,
else.
that's what I'm talking about.
does default calendar have leap years or not? Is that a-
You can pick that, I think. Yes, you can pick that.
Because sometimes it's confusing. Sometimes people don't realize.
I know.
Some models have leap years, some models
Yes,
don't.
yes.
I saw the ROM's
Yes.
model initially that does not have the leap year, right?
The ROMs doesn't think
Doesn't
about
care,
time, right?
yeah.
Only how, like seconds, minutes, and days. You compute up
Right,
to your
right,
convenience. That's
right. It
why-
doesn't care.
It doesn't care,
You don't
yeah.
have a solar cycle.
But in this case, it does because you give it to him,
Right.
right? So in
you
this
have to
case,
build
you are
it.
the one who are in
Yeah.
charge of setting the clock.
Right.
And so that's what we did. In this case, the ocean surface in albedo is spectral. That means there is a formula that changes with latitude, and it's based on spectral components. It's not a constant albedo like you usually use in WRF. You have the option of using a constant albedo. So it also tells you what compilers it's using, flags, what library it's using, and it will tell you Cresm will be built in this directory, will be installed in this other directory, and please go ahead and check ROM's header file because before you type make, it's always usually works, but it's always good to check it. Also, you can change make file and make comp if you want to do further refinement, but otherwise, and you can type make help for additional options. Usually, those are okay. So again, which models are we using? Again, the WRF ROMs. We have hydrology that is included in CLM. We have, some sort of model that tells us what the infiltration of the soil is. It's called variable infiltration capacity. So it's based on saturations, basically, of the top layer. Not just the top layer, but it starts from that. Anyway, let's see. So we started with this. This is where we are. And, you can pick, and then this is where we're planning to go, hopefully. We can introduce some data simulation capabilities and maybe a biogeochemistry module. And then there is the option of introducing waves, coastal circulation, and hydrology as well. So that's the plan. I think that's what we have in mind, but it's going to be a long run.
Vic is already like hydrological model. Right?
It's a very simplified model that is inside CLM. Now, this is Vic, it's a module, it's not a model. There is another model that is called
Even
Vic.
the hydrology will probably go into the land surface.
Well, it depends. You can use WRF Hydro to some extent. You can use the SWOT model from A&M, which was the other option, but we haven't included.
Data assimilation, I'm sure.
But that's a PC code, right? Did you actually get it?
No, we can.
Did you actually get it? Or the
Um,
the code itself?
I
or
looked-
just,
I looked at the. I don't think I looked internally at the code, but I looked at the files. Yes.
Why would data assimilation go in the coupler? Because it requires a full model state.
Yeah.
Why would you put it in the coupler?
Because we're trying to do
The observations.
couple of data simulations.
I don't think the
Not quite
couple-
sure
yeah.
whether- We don't know whether it needs to go to the coupler.
The coupler
Right.
deals with the interface.
Yeah.
But data
So
assimilation, you need the full atmospheric state.
Right, so it's
we
a-
need to do, I don't know how to do the couple of data simulation.
Yeah.
I mean, how are you going to, what are you going to call it?
But I'm thinking, I'm sure NCAR DART includes.
I know I'm actually talking to them about this.
In fact, that's something, and he wants to spend some time at
Yeah.
NCAR.
I have a project that
and,
we'll see if it will be
They're doing
approved.
all kinds of data assimilation.
Yeah.
Putting the couple of data
Yeah.
simulation module into that.
Yeah.
Alicia is working on that.
Right. They're doing decadal prediction. So,
That's right. So she's actually, if this thing going through, and she's going to be on this project,
okay.
she's going to be working with us on this.
So she's the one who gave a talk at the meeting last year saying ocean data assimilation is really bad.
Well, the really bad is I'm not necessarily, it's nothing to do with the, yeah, it's just the data quality
Data.
problem. It's the problem itself, not necessarily with
So
methodology.
her results showed that the paper just published recently. Her results showed that the hindcast model has better state than assimilated.
Well, that's the reason why NCAR, they refuse to use data simulation for their decadal forecast, and they just run the model forward and using that as a cost.
Just use the surface forcing without any.
Mhm.
But for our problem, may be different, because we're looking at
Regional, it's possible, yeah.
Yeah, because regional, it tends to have a more data coverage near the coast and in the region.
Yeah, yeah,
That
no,
might be
yeah.
worth pointing out that most people do global.
Right. I mean, for example, in Gulf of Mexico, I'm sure there are lots of data you can use, right? I mean, compared to the-
Yeah, I don't know how good, I don't know. Yes, but
I mean,
I don't know.
I hope that there's something.
yeah.
That's worth-
I mean,
So,
Also, global data estimation, like Tomohan
I know.
circulation, ice, they really mess up.
so do you have an example to show us?
I want to just, because we only have 4 minutes left, 3
Okay.
minutes left actually.
Okay.
And so quickly, I'm going to go through some highlights which are not very high. And so I wanted to show something about, no, nothing else specific.
You actually run the case, you run Xiaohui's.
Yes, I did. I don't have that here. I
You
wanted
don't
to,
Is Google
I
Earth,
wanted to skip it. Yeah.
Did you run Xiaohui's experiment using the coupler 7 or the physics or the Wolf physics?
I think I used the word. Yeah. Yeah, I think actually I did both, but we never. You remember I gave you both outputs at some point. We never really looked into it. Okay, so I'm going to show you something in some simulations. Recently, we've been focusing. We already used this model in the Gulf of Mexico, for instance. We kind of use it partially in the North Pacific, and now we're focusing in the Atlantic. So the original project included basically this domain. It was a basin model. And now we're focusing in this area, trying to see, actually, would be the new domain, trying to see if we can find a reason for the model biases. And so this is a spin-up simulation of the ocean, which I needed to do to run the coupled simulation. These are some preliminary results, which were presented in the CSN workshop. We actually find results which Chris found before in terms of a wet and dry bias when you change the radiation scheme in WRF. So those results have been confirmed with these couple simulations too. With this scheme using CLM and NOAA from WRF, you can see there's 3D nudging too in the ocean model. I ran a twin experiment, which is not going to be good. You see the bias developing as you move forward from January to June and forward until October. So we still have a positive bias in this case, but the atmosphere we used, all the parameterizations were not the best ones. Those were parameterization for a very old run, and we needed to use it as a reference. They're not the ones we're using now. So don't think that this is actually the result. But this shows that once you couple things, then you start seeing feedbacks, and it's very hard to predict where the model is going to swing, in which direction. This was done, just a fraction of it, done with the NOAA instead. At some point, some of this setup blew up in WRF because, again, the atmosphere wasn't configured in the best possible ways. They're kind of similar. If you switch between this, you look at April, for instance, and NOAA. There's some differences, so you'll see some feedbacks already. This is another configuration we're actually using right now for the southeastern Atlantic. And so in this case, you see the bias. We start with models that have been spun up, and the ocean actually includes very little bias at this point. It was forced with WRF. When you couple, you get a negative bias. So it becomes colder instead of developing a warm bias. And we're still trying to figure out why.
But there was an issue how we spin up the ocean.
Well, the ocean was spun up with WRF 9 kilometer, and this is a 9 kilometer.
Right, but the way
simulation.
we forced the ROMs was using the ball formulation.
Yes, it was totally uncoupled. So of course, things are different.
That's the problem.
The surface layer is not consistent.
We're
Yes.
trying to redo this.
Yes, but that's, as preliminary results, that's what we got. The point is, when you couple, you have a lot of feedbacks that you don't expect. And this is the result, at the end of the year. So there's probably something wrong with that. So we also changed radiation scheme, and look at the difference. This is pretty clear that there is a effect from the shortwave radiation that influences this type of bias. And that's it for today. I think we are just on time. So it was just an overview. And if you have questions, just let me know. Come see me.
Very good. Thank
And,
you very much.
Sure. And
And
questions now?
I think we need some volunteer to test this model. Who wants to use that? I know Xiaohui wants to do. In fact, we're trying to rerun her more specific case. But we want to right now the one she has right now is a 9 to 9.
Yes. You want to do
And
27
remember,
tonight?
we fixed the lateral boundary condition for long.
Yes.
Now the model is
Yes.
actually being better. So, but the 9 to 9 may be too expensive, so we're trying to configure it in a 9 to 27.
Yeah.
So maybe since this thing is quite ready, maybe we should start with this rather than you. One of the issues is that you don't have the filter yet, right?
No, yeah, that's true. The filter, the SST filter is not here.
How
It's not
difficult it is to put in a filter?
Well, I was planning to do this as an external option so that you don't have to use ROMs necessarily.
How long is it difficult?
It takes some time, yeah.
Yeah, because the
It's not difficult, it just takes some time.
because the tiling issues, right? Because you have to redistribute it.
Well, you have to insert it. It's like an external component. So you can either do it at the driver level
Yeah.
instead of at the model level, like we did with CRCM, because it was much simpler. So that allows you to also
So the
filter
question
data.
is that
also.
if we adopt to this version, because we do want to run in parallel the filter versus non-filter, it's going to take some time, of course, get a control run configured and run first. But maybe it's okay. I mean, maybe you can start with the control run first and then wait until the filter.
Well, the thing is,
Does that has any estimation of how long it will take for the filter to apply in the model?
Right now he's busy with
No.
teaching, so probably
It depends on
end of
the
semester.
remuneration.
It's probably looking at May or maybe end of May maybe.
Try to get to May first, survive. Then we'll see.
Okay, I have a question still. I'm not quite clear about the flux computed by couple 7. It is
It's very
different
simple.
from the flux computed by the Wolf surface layer scheme, right?
If you want it to be, yes, you have the option of using a different
Also,
standard.
it is different from the flux computed by the bond formula in ROMs, right?
Yes, that it is.
So it's like if we have the same the temperatures, the humidity, and all these things, if we use the same input and then we compute it by the Wolf surface layer, by the couple 7, by ROM's formula, we'll get 3 flux output. And
probably,
they
yes.
are different.
Probably, yes. The underlying theory is the same as the Monin-Obyukov, but the parameterizations are different. And so, in the way the theory is not closed. So you have to close it and you have to iterate. It's not a closed formula.
I think we probably just want to stay with our home. I recommend that we just use the Wolf computer flux.
Even Wolf, you can use a revised MN5 scheme, which actually is more stable than the original MN5. Problem is, when you read the paper, usually those things are tuned on data sets, and they only represent one portion of your choices. Then, when you run this model in an area in which really the bug formulation wasn't tuned for, like the core was tuned probably in the tropics or something like that, then you get what you get.
I think the coupler 7 version of the bug formulation is probably very close to the ROM's bug formulation, right?
No.
No?
No, not at all.
Why
The
not?
theory is the
I
same,
thought-
but-
I thought it was large and Steve Younger actually put into the coupler.
They did. But
So it's all based on the ocean formulation. It's all based
Yes,
on the
yes.
Toga core project.
no, really, because here's the difference. We have a model, right? So everything comes from the model. So the surface layer is the layer that sits between the lowest atmospheric layer and the surface, the real surface. you need to replace the whole thing, which means the input comes from the lowest atmospheric layer. When you use a bulk formulation that is tuned on data, from data, like the TOGA core experiments, you use surface values, which means 10 meters or 2 meters. And the parameters they use, they're tuned for those quantities. Now, when you run a layer that is thicker than that, there's no guarantee that you're going to get diagnostic values like T2, Q2, or U10 and V10. They are consistent with the experiment. So it is a different
No, but
animal.
what about the physics of the formula itself?
The physics is all the same, but what the parameters are, the way it's formulated is different. The way it's implemented is different. The ranges allowed, for instance, for the turbulent functions inside are different depending on the scheme.
It's really surprised me how
So-
much difference it makes.
I don't know. I mean, we saw a lot of difference.
The runs
If you're
you
going
show
ahead, some point of time, we have to do some sort of a real.
I think we need to do.
Yeah.
a
Based on
systematic-
besides some simple experiments,
Right.
follow through 3 configurations, like the couple 7 or.
Well, that's the reason why I recommended that, using the data ocean to run the ROM or WRF itself. So that's the best way we can see it.
Right.
And then we can see the flux, how the flux was.
So I still think just doing the column model, right, not the whole 3D model. This is a question.
Well, the column model,
There's a single.
Well, the column model doesn't have any feedback. The good thing is it doesn't have any
Yeah, and
feedback.
it's also,
So-
so you can run it on your laptop.
And in fact, this is what
Because
I was planning to do.
Because by the time you run it, you get a bias, it's sort of convolved. Things affect each other. Your objection is based on a column, a fixed boundary condition.
No, it's a good idea. I mean, that's what I was
So
planning
no
to
point
do.
running a
Absolutely.
global model.
At least that's
is
first
there-
thing.
Is there a column model actually?
I built
Yeah,
one.
yeah.
You have to, well,
built
the
one.
one you have is not even a column model. Your
No, but-
one is really just the
It's a,
surface.
yeah,
It's
the
just the
column is not
surface.
the full atmosphere.
Right, it's
Sure.
not the column.
But-
What he meant column model was actually the entire
No, but
column.
No, I
there's a
think he's
better-
talking about the
better
profiles.
column model for CAM.
Yeah.
CAM has a companion column model. People use it.
But again, you don't have to
Warp models,
use
they
the
don't,
full
I don't
atmosphere.
think we're wrong or war has a
Warp
column
may
model.
not, but what you can do is take the CAM model, put that stuff. The CAM, a single column atmospheric model is very standard. That's how NCAR people tune their.
Well, but that,
It doesn't really
that's
matter. I
something we
mean,
can-
I
that's
only
something
need
we
some
can-
data.
right,
know,
but
that's
that's
really
something we can talk to NCAR people.
Right.
But that's how they tune the convection scheme.
But I think at some point, it's useful for you to, maybe we should, if this collaboration scene is really going to happen, right? So we should invite people from NCAR
Yeah.
here. And you can give a talk on this, we can all sit here and then, or we can go to NCAR, visit them and then giving this talk. And they'll be, now they actually officially a
Mhm.
partner, so they should pay attention to what we're doing, right?
Anyway, so I don't know if
Basically,
there
we need to get
is.
that time.
Uh-huh.
We need to get that time to discuss something.
Well, that's, I think that if Bill Large sitting there, it thinks the
Yeah,
CDD
you're
director.
not saying something.
Right, that's right.
I don't know if they can
You guys come to the
no, you
meeting,
cannot
come to the
see.
meeting, right? Yeah. Bill Large is very much behind this.
So if he says come to the meeting, then.
So I don't know if there is questions from the other side of the internet.
Is Chris there?
Yeah.
Chris?
No questions.
Okay.
Okay, then I'm gonna stop this. Thank you for attending.